So today's discussion is all about just a continuation of the previous one. Today we will discuss three-phase transformer, different phasor groups. Namely, we are indicating the balanced operation of the transformer with 6, 11 and 1 position. So, first of all, let us study what about Y6. So, in Y6, it is very simple to realize that suppose if I give you one transformer A1, A2, B1, B2, C1, C2, and then I short all of them to form my neutral. Then this is the primary or high voltage side denoted by the capital letter. Now let me draw the winding for the secondary side. So unlike the primary, here what I have done, I just short the secondary winding, and accordingly the different terminal of the secondary winding. So if your primary phasor is like this, secondary phasor would be right. Now let us try to realize DD6. Obviously, as I have mentioned, that you cannot have YD6 or YD0 or DY0, DY6. It is only possible when your primary and secondary are having either same configuration, or it is possible to realize it with delta zigzag case. So let us see this. Now, in case of delta transformer, what should we do? Delta, let us take so for DD6, what you should do? Do remember one thing, that in delta we never connect A2, B2, C2 like star. We always connect one with the terminal of other two. So A1, B2, B1, C2, and then finally A2, C1, right? If this is our primary, then how to realize the secondary? You can write it like A, B, C. Like the means case of star, we consider primary terminals with subscript 2 is our supply terminal. So here also you can do that. And now for his side, what we can do? So if we try to reverse it, what should we do? Just reverse the pattern. A1 with B2. Now you connect A2 with B1 and B2 with C1 and A1 with C2, and then you feed or rather collect your secondary supply from this terminal. So that would give us the configuration that is DD6. Now the question here is that can we realize it by connecting it in some other way, like here are we getting the exact 180-degree phase shift? Let us check. Say this is our A2 A1 B2 B1 C2 C1. One thing I would like to make you understand that in this earlier case also, here if we just mark it, what we will get A2 A1 B2 B1 C2 C1. Now while connecting it in delta, you can consider that I am doing this. Right, so we are following this same sequence while connecting it in delta. And what about this one? Here it is like A2 is connected with, so here it is B1. One more thing here you should note that we are assuming that the transformer primary and secondary, they are in phase. Here we are not considering the polarity while drawing this phasor diagram. We are considering that they are in subtractive polarity. That means whichever primary side voltage you will get here, the secondary side voltage will be just a similar means a phasor of same orientation, only magnitude wise different. Here while drawing the phasor diagram of three-phase transformer, we are considering our transformers are ideal in nature. Of course they are not, but in order to draw a simple arrangement and simple diagram, we are doing this. So this is DD6. Now let us try to realize DZ6. That is very interesting. So DZ6. It is like Oh, sorry. Now, how to connect them in delta? Let me use different thing to make it clear. Short A2 A3, B2 B3, C2 C3, and then you connect like so this is A, B, C. Now what about Z? Z will be like the same thing. So how to connect them? First let us draw the phasor diagram here. That is A, B, C, and we are maintaining the same start phase sequence. Just relative position in the space is somewhat different. However, here as it is in delta, in order to figure out what we need to do, we have to draw, as I told you, we have to form a star inside this delta. Now, what we are looking for? We are looking for a phasor that is like this is like, if these we call in, then that should be now how to realize them. First, let me draw the corresponding phasors here. They are A4, A3, A2, A1, just a minute. They are, let me draw them here so we can easily use them as per our need. So now how should we place them? The big question is that how should we place them? Now I was just drawing this figure correctly so that we can utilize it without any further issue. See, here A4 is connected with the voltage source. So definitely if you want an 180-degree phase shift, you have to connect your terminal with A1. So how to realize that? And do remember that our phase cannot change their orientation in the space. They remain same. We can only just shift them from here and there, connect one terminal with another, but that doesn't make their relative orientation, any change in their relative orientation, means their orientation remains same. So if you just draw them in line, then you will find that this one will give you something like this. Right, now what about the other? Similarly, this is for B phase, so we have to place here B1, B2. Like if you connect A1 with your take out A1 as your secondary lead, obviously this should be the case. Now so this is our B1, B2 phase for B1, B2. Now how to connect them? Take this A4, A3 here. And if you can do a correct connection after connecting, you will see that it will be, in case of zigzag or whatever, you will find an means evenness inside this diagram. Means the diagram, it is not like for some phase you have connected some terminals with one, and for other phase you will have a different terminal connected with one. It will not be like that. So now what I was talking about, that symmetry, here see for all three phases for zigzag I am connecting it from A1, B1 and sorry, what happened to C1? I have made a mistake. Yes. Yeah. So how to connect them? Yeah. It should be like fine. Now it is. It looks good. I was talking about symmetry. Now you will find there is a symmetry. How? See, this is for every phase. Here B4 C2, here A2 C4, here B2 A4. Right? For every phase we are connecting it from A1, B1, C1. Then all three C3, B3, here A3. All these are connected to form your neutral N. So let us connect it in this way. Now let us first make this terminal A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, and then let us connect. So A1, A2 should be connected with C4, C3. So A1, A2, we have to connect it with C4. First of all these A3, B3, C3 must be shorted to form our neutral point in now A1, A2 with C4, then B2 with A4, and then obviously B4 with C2. So these are the terminals. We are getting DZ6. Now we will consider the cross one. Cross one means say DY11 or YD11 or DY1 or YD1. So why this phasor group is important? Because suppose if you want to perform parallel operation of three-phase transformer, then you have to take care, like you cannot connect DY11 with DY1, right? Because your secondary side will be of different phase and it would result in a catastrophe. So you have to make sure that all the parallel during your parallel operation of transformer, all the participating transformer must have this same phasor group. Unlike you should not connect DD6 with DD0. In that case also you will have that kind of a huge circulating current will flow and you will have accident. So now let us try to develop dy, just let me check, yes it's recording, dy11. So what is dy11? Let us have this winding. I mean hurry, though I am just doing a rough sketch. If you try to understand, then you should draw a neat diagram. That would be helpful. So A1, B2, B1, C2, A2, C1, and here we are giving A, B, C, and let us draw the other end. Now let us see what we will get here. Here it is our A2 is A1 is connected with B2 and then in this way. So you can draw the diagram like A2, A1, B2, B1, C2, C1, right? Now here we are trying to show that DY11 configuration. Just for this, let us develop a 52S star connection inside this delta, whose line voltage are equal to the voltage of this delta. Here it is A, B and C, right? So if that is the case, now if you just draw it like then what you will get? So if you map it here, then you will see that the secondary is having a difference of 30 degree. Now if you just rotate it, rotate the whole thing, let me just draw the blue line. And how is your secondary? That means secondary is leading your primary by an angle of 30 degree. So it is dy11. Similarly, you can have yd11 also. And let us now have dy1. How to realize dy1? Right. So what is your phasor diagram here? Now this is your A, this is your B, this is your C. So what you are having here, right? Now here if you draw the same thing, right? So then what you will have corresponding phasors. However, this is not the phase sequence. So if you want to make the phase sequence correct, then what you need to do, you have to make the whole thing rotate. So rotating the whole thing will result in what? Will result in this, like it will become something like this. Now again, this is your A, B, C. So just like the previous one, draw the your star inside this delta whose line voltage is equal to the delta phase voltage, and you will see that the primary is leading the secondary by an angle of 30 degree. So this is the whole thing. So here, instead of doing all this kind of means drawing, let us solve a few problems that would enrich our understanding in this particular subject. So here, a bank of three single one phase transformer is connected to 11,000 volt. Let me write. It is 11,000 volt. Volt we are having, and takes 15 ampere. If the ratio of turns per phase is 10, calculate secondary line voltage, line current, primary and secondary phase current. So secondary line voltage and current, primary and secondary phase current. So how to solve this problem? See here, first of all, four configuration are mentioned: start star, delta delta, start delta, delta star, right? So let us start with one, that is start star. It can be 00 or YY6, but that won't. So what is primary phase voltage? For start star, primary phase voltage so that would give us something 6350 volt. Now what is primary phase line current? Since it is star, so line current is equal to the phase current is equal to 15 ampere, right? Now secondary phase voltage, do remember, whenever you will handle three-phase transformer, always consider phase to phase conversion. Never ever try to do anything with line, even if you know the line transformation ratio and you are smart enough to handle it, but it is always advisable that you handle all the phase data and then you find out the line data. So ratio of turns, so it is 6350. What is ratio of turns per phase? It is 10. So 6350 by 10. So that is equal to 6354. This is secondary side phase voltage. Now when secondary is in star, so secondary line voltage would be how much? Basically I am doing this problem just to means quickly recap our lesson on three-phase connection. So secondary voltage would be something like now again as it is star, so secondary phase current is equal to secondary line current, right? Secondary phase current is equal to secondary line current. Now what else we have to calculate? The secondary secondary current. So secondary current, obviously here also you should handle the phase information. So if phase voltage is attenuated by a fraction of 1 by 10, so current voltage will be current will be amplified by, so this will be the secondary current, that is 150 ampere. So what about the output? Output kVA will be √3 into VLS into ILS. So that would be √3 into how much? So it will result you 285.8 kVA. Actually what we will observe here is in all these four cases we are going to find out it would remain 285.8 kVA, because this is basically the individual kVA capacity of the transformer multiplied by 3. Individual kVA capacity of the transformer is how much? It is 11,000 into 15. So 11,000 into 15 if you do, you will find something like, where is my calculator? Where is the calculator? Just a minute. So yes, I got my calculator. So what is your one transformer kVA? One transformer kVA is how much? (6350) into 15. So if you do this, you will get exactly same as you do this, you will find this same thing. There will be no change. Now let us investigate the same for whether it is delta delta. As I told you, my objective here to solve this problem is that to give the student confidence that problems are solvable. primary, in case of delta, primary line voltage is equal to primary phase voltage is equal to 1000 volt, primary phase current since it is delta connected, so you have to do it by root 3, so that would give you 15 by root 3 is equal to 8.66 ampere. So either way you will get the same answer. If you do 3 into 11,000 into 8.66, that would also give you that 285,800. Now what about secondary? Secondary is also delta connected, so secondary line secondary phase voltage so what you should get it here, it is 11,000 by 10, that is 1100 volt. What would be secondary current? So secondary line current secondary output right. Now here in both cases, first we consider star and then we consider delta. So what you can observe here, or here the line current in phase voltage, phase current always maintain that turns ratio relationship. However, in case of line current and line voltage, here they have maintained that ratio. Like if your primary current is 15, the secondary current is becoming 150, even if we consider the line current. That is because both the primary and secondary are having identical interconnection. But if we consider star delta, then we will have some different result. So for YD, what is the primary phase voltage? It is just like the star one. In that case of star, it was 6350. What about primary phase current? Same as line current, that is 15 ampere, right? So what about secondary phase voltage? Secondary phase voltage would be how much? 635. What about secondary phase current? (150 ampere). Now what about primary side input, that is root 3 into 11,000 into 15. What is secondary side output? Secondary side output is root 3 into 635 into root 3 into 150. So basically you are going to get the same result, right? So that's all. Here also you will be getting 285.8 kVA, and similarly you can verify for the last delta star problem, you will also get the same result, right? Now so here first of all we are having a problem, but before we solve that problem, let us discuss something very basic of three-phase impedance. Like if you have three impedance like this, I am missing Inco 2, but I couldn't help it. And if you know that now if you try to convert it in equivalent star, the idea is that between the two terminal point, the resistance or impedance should remain same after the conversion. So as the primary side is balanced, so secondary side should also, you can consider it is balanced. So it will be having, say, every phase is having ZS, ZS, ZS. So what you can write from here, it is like 2 ZS, right? And how much is 2 ZS should be, if you consider from this side, it is in this case it is ZT parallel to 2 ZT, that is 2 by 3 ZT. So 2 ZS is equal to 2 by 3 ZT, that means ZS is equal to 1/3 of ZT, or 1/3 of, that means RS is equal to 1/3 of RT, and XS is equal to 1/3 of XT. Right, now here what is the problem? Let us read the problem once again. A 6.64 kV by 400 volt 75 kVA transformer has a series resistance of 12%. We have to calculate the reactance in ohms referred to LV and HV sides. We can drop this first part because that is of no use. 3 such transformers are connected in star-star. Calculate the line voltage and kVA rating. The second part is for important to us. So second part, what we can do, second part. To suppress this limit. So here it is the second part is important for us. So how to solve that second part? Second part could be solved like what is the secondary primary side, or not primary, what I told you that we should consider the high voltage side. What is high voltage side voltage? Now individual transformer are having 6.6. Now if you connect it in star star, so the high voltage side voltage will become root 3 times into individual transformer high voltage side voltage rating. So root 3 into 6.6 into 10 to the power 3, this much volt we will get. That is almost 11,000. And what about line voltage of LV side? Now, what is the rating? Rating should be 3 times of individual rating. Right? Now, what about the per unit reactance of the bank? What we can write? So it will become how much? It is it was given, but if you solve it in their problem, they have find out in part 1 the reactances. So if you solve it, you will still get, which is same as the individual per unit reactance. Now we have they have asked us to repeat the problem when the bank is in star delta connection, but you will get the same result, right? So there is nothing much in this problem. Just let me. So now let us consider this problem. A bank of three 660 440 volt transformers is connected star delta with additional tippings at the midpoint of the secondary winding. Determine the magnitude of VAB, VC VCA, so obviously VAB VBC VCA will be half of the total. Now part A, currents of 100 ampere at unity power factor are taken from A, B, C, and currents of 100 ampere at unity power factor taken from terminal A, B, C. So first of all, let us draw the phasor diagram. The phasor diagram would be like, it is first if you consider this as reference, so this would be like this is your VA, VB, VC. Now how to draw VAB? Very simple. What you need to do? You have to draw that is exactly this is minus VB, and what we know that VAB is equal to VA minus VB, so that would give us VAB. Now in case of the delta side, what you will get, the voltages, that is delta side voltage will be VAB, okay, use white, like this is VAB, sorry, this is star. Let me use Y to introduce means indicate that this is for primary side. So you will get VAB, then exactly 120 degree apart you will have VBC, and exactly 120 degree apart you will have VCA. Right. Now what about your small voltages, like what you the tapping in between? If you have difficulty, what you can do, you can try to understand in this way, like but this one, since this is YD and from primary you should use primary as reference phasor, here it will make you a bit difficult for you if you try to follow this in this fashion. So better you try to understand that whatever AC you will get here, that should be, if you mark them like A, B, C, so this whatever AB you will get here is exactly same as this AB, right? So in that way you can find out the voltage phasor. Like if we can form a fictitious delta winding by connecting these 3 points, then this one and this one should have identical voltage. Now what about V small AB? See V small AB. See the position of V small AB. How to get that V small AB? If this is VAB, here it is your V small AB. Now if you just draw a triangle and means divide them just by basic geometry, you can understand the length of this AB is half of, or the distance between A and B is half of this capital AB. So what you can get here is that it is this is VAB is equal to magnitude of VAB is equal to half of, and VAB is that is 180 degree out of phase. Similarly, you can construct VBC and VCA. Fine. Now, what is the magnitude? Magnitude, obviously, if they are of this side is 440 volts, so between A and B you will get 440 volt. So therefore, all these magnitude wise should be to 20 volt. Now here the current of the winding due to this I, let us consider that this one is I and here all these are I dash. So current due to this I, every phase will carry how much current? I is the line current of, you can say that it is like the outer delta. Now, what is the phase current? Delta side is our secondary side, so delta side is how much? I by root 3, right? Now, the I by root 3, it is the power factor angle is how much? It is unity power factor. At first problem, it is unity power factor. So all the they will follow their corresponding phase. Like what we can write, here this one, this IAB will have the same current, or better to say like this, what I am trying to say, let me write it here, that angle between right. So whatever be your current, phase current, that will maintain our voltage with the phase voltage. Obviously line current leads phase current by an angle 30 degrees, so you cannot apply this concept here on the line current. Now here let us consider this, that this current will lag behind an angle of theta 1. So first case it is unity power factor, so theta 1 is equal to 0. Now we have to find out the I second, means that I dash, that is we are taking out from small a, small b, small c terminals. So small a, small b, small c terminals, they are having VAB, VCA and VBC. So what we can write, that for them, in this phasor diagram, let us draw IAB. Although it is exactly in phase with first problem, it is unity power factor, so it should be in phase with that one, but let us consider that it is having some phase, some arbitrary angle theta. So the current will be yeah. Now similarly we will have all this is for I. Now we have to find out I dash. However, in case of this I dash A, I dash B, I dash C, here you have to understand one thing, that here one part of the winding it flows in I dash small ca, another part is flowing in I dash capital BC, right? So what you can understand that when you are trying to think about that I dash AB, that should be is equal to like here if you see that this is I dash AB. Now what about this I dash AB? What can we conclude about this? Like if we are claiming that here this is the current, how to explain, that here the current is I, right, and here also it is I, here it is I. That means the current that is flowing through this is I by root 3. I by root 3, I by root 3. When all these is equal to 0. Right. Now when these are not is equal to 0, but you are interested to keep your current constant, then what you can conclude that I dash AB is equal to what? Is equal to here this current, this one, well, so I took some time to draw the diagram of this complicated problem. Here, you first read the problem and try to understand it correctly. That here it is saying that for the means the total delta means that ABC, we won't have any problem. But this is the second part is complicated, that having this means midpoint, voltage of the midpoint, even intuitively we can understand that voltage will be, if this much is 440 volt, just by applying the property of like that geometric and basic trigonometry symmetry of triangle, we can find out the voltage would be 220 volt in every case. But what about the current? Now for finding out the current correctly, what I have done, I have drawn the picture. So here it is your phase current IBA, IAC, ICB. Now one question may comes in your mind, that why it is IBA when we are talking about phase angle. Why means what is our notion for normal phase angle? It is like this is what we do. So normally we should write VAB, and in addition we should draw phasor for IAB. But if you notice here, I have drawn the phasor for IBA. The reason is that it is the terminal, means what you are getting, you are getting across the load, but across the source will carry the current just in opposite direction. Right? If this is your load 1, then the source current must carry a current minus I2, so that you can get this much angle, and your source power should become means source active power, you will get negative amount, and for load you will get some positive power, right? So here this is IBA, this is theta 1, then what is that? This is a complicated problem, please pay your attention. Obviously IBC and ICA all are theta 1 degree lagging behind the corresponding voltage VAB, VBC, yeah. Now here what is happening, that when we are talking about I dash, this I dash is very troubling. Like, why I dash is troubling? Because in order to find out one I dash, you need to find out I dash CA and I dash EV. Now what about I dash CA? For finding out I dash CA, you have to draw the phasor of VCA. VCA is the phasor for I dash CA. Now you may ask me, what is the logic behind drawing this VCA here? So sorry, it is VAC. We have to then we can find it out. Like here you can see it is the phasor of VAC. Sorry, VCA, right? Now this VCA, how you are finding out VCA? So if you let me write the equation, otherwise you will get confused. V small c A is equal to how much? It is like right. So this voltage yeah, so this voltage will help us to find out, and what we will get, that this VCA, that will be just exactly opposite of, okay, let me just show you that. First of all, let us try to find out VCA. So what is VCA? It is right. Just a minute. Well, so here first let us try to understand from a very basic instead of doing step jumps, because I'm also having problem in doing such step jumping. Let us write it one by one from very beginning. Take us the total this outer delta. What we can write from here, that VCB plus VBA plus VAC is equal to 0. This is by application of KVL. Now, if that is the case, then what can we write from here? VCB is equal to
if you just do the side transposition, what you will get? You will get VBA minus VAC. So this you can write it like VCA minus VBA. Right. Now, if we are interested to find out VCB, small VCB, so let us write small VCB. The more small VCB, we can write it like by taking this blue, this interior delta. We can write VCB, as this is a balanced load. Obviously, the whole winding is balanced and maintaining symmetry. We can write VCB is equal to, following same notion, we can write VCB, or you can take VCA. VCA would be how much? Here also we can do it for VCA. Let us do it for VCA. First VCA plus, okay, then it should be VAB plus VBC. So it would be like VCA minus VAB minus VBC. So what we can get from here, it is like VCB minus VAB, right? So similarly, here we can also write, taking this inner delta, as this is a balanced winding, we can write VCA is equal to VCB minus VAB. Fine, agreed. Now, what is your VCB? VCB. Now you take this delta. So from this, what we can write? VCB is equal to minus V B capital A minus V capital AC, right? Similarly, for minus VAB, right, we can take this triangle, so we can write this will become plus how much? VAB, so it will become plus VBC, sorry, plus VCA. VAB, we will getting VBA, VCA, right? It is, we can write it like VCB, VCB, VBA, VAC. Okay, and here it is VAB. Then it should be VBC. Then what it is? It is VCA. Well, so these two, VBC and V, these will cancel out. Fine. Now, what we are getting? I think I have made some mistake somewhere. is VCB minus A small c. So it is giving us V CA. This is what? Sorry, here also I made a mistake. It is small e. We started from here, VCA, then we are getting this VCA minus VAC. So
Okay, so I just found it out that simply we can exploit the basic trigonometric relation and we can get the result. Like if you see the VCB, if you consider the triangle with vertex capital A, B, C and take this BC as the connecting line, BC is connecting the midpoint of the arm AB with arm AC, then what you can write that magnitude wise VCB is half of this VBC. However, the direction of measure, it's just opposite of this, so you can write it is minus V and the second one, the AB, the way you are measuring here, it is just opposite, so you can write, and that is how we are getting it is minus capital VCA by 2. So that is why we have drawn it diagonally means V small ca is 180 degree apart from V capital Ca. Right. Now how to find out the direction of current? Like the previous case, similarly here also the current is exactly theta 2 lagging I dash BC. What is I dash small bc? I dash b small c is like here you can write it is same as I dash a capital B. So I dash b small c is equal to I dash, like here the current is coming and it is going here. Now what is we can see here that this current is making an angle theta 2. Similarly, we can find out the angle IC dash A. This is I dash CA. Oh, sorry. This one. Actually, so many angle I dash CA is equal to
I dash AB. Okay. Now similarly, this should lag BC by an angle theta 2. Agreeable? Now their resultant should give us the current. However, we are not going to find out their resultant because their resultant is actually the means if you just subtract this I dash CA from this one, then you should get I dash. But we are not going there. What we are trying to see here is that we are interested to solve that problem. So that problem, so it is 220 volt, angle is also opposite direction. Now on the first part, that in the first part it says theta 1 is equal to theta 2 is equal to 0 because both are unity power factor. So what is your IBA, that red current? If this one is 100, then IBA should be 100 by root 3. Now what about that another part? This I dash is also how much? I dash is also 100. So what we can say that this will give you 57.8 ampere. What about the other one? ICA dash. Oh God. I dash C capital A. What is I dash CA? This one is equal to I dash AB, or any other current because this is balanced, so you can write I dash CA now. This is okay. Now here what we need to find out, the primary current. Now while finding out the primary current, think about something I would like to highlight here, that in primary current, while you are finding out, we are assuming this is a linear system, so we can apply the concept of superposition here. Here you can see that this current, whatever is flowing through this winding BC, suppose this will you can understand like the way we have constructed our delta star. Like suppose this one is, what is that, A2, A1, C1, C2, B2, B1. So basically this is what? This is C2, C1, this one is B2, B1, this one is A2, A1. Fine. So whatever voltage you will have here, just let me clean this first. So what I am trying to say, here one component of current that is flowing total, and that is 100 by root 3, that is for this I, right? This I. Now what about the other current which is flowing here, half? That is how much? The magnitude of that current is also 100 by root 3. However, try to understand that this is C1, C2 winding. So for this C1, C2 winding, what you will have here?
you will have 100 by root 3. So this 100 by root 3, it is completely flowing through here, so you will get here accordingly. Now what about this 100 by root 3? There is another 100 by root 3 is flowing here, and they should be 120 degree apart, means apart in time phase. Are you getting my point? So if that is the case, then how to implement that? Two are current 120 degree apart and both are having 100 by root 3. So basically, if you try to find out their resultant current is the current that is flowing through this. How much you will get? Say A1 or A square plus A square plus 2 it is actually okay. So what you will get, let me write down the formula here directly. Or otherwise, what you can do, instead of considering this 100 by root 3 two part, one thing you can consider, like this phasor, this 100 by root 3, this will need to be counterbalanced by which one? This one. So this 100 by root 3 is like how to transfer it. Let me show you how you will get. For the first part, it is that we are taking two current. One is when we will write MMF balance considering ideal transformer. This is for one, magnitude wise I am writing. Another one is how much? Right? So here, when you will try to find out what, but one thing that is common, that two secondary current, so your net current will be how much? Primary current. If I increase the primary current, I1 plus I1 dash will be N2 by N1 I by root 3 plus N2 by 2N1 I dash by root 3. However, one thing is good among them, that they are, for the first case, they are in phase. So if they are in phase, therefore what we can write, the both of the current are at unity power factor, so that would be something like 57.8 N2 by N1 is how much? N2 by N1, from our problem we can find it out. It is 6600 by 4400, probably 15. So it is 57.8 by 15 plus 57.8 by 30. So you will get 5.78, right? So 5.78 when you will get, then you are having what? So here when you are having this 5.78 is the primary current for the first case. Now for the second case it will become more complicated. This is when this is for I UPF, I dash UPF. Now we are going to the second part of the problem. In the second part of the problem, what they have said here, theta 1, theta 2 is not 0. Theta 1 is how much? Cos inverse of 0.8. So cos inverse 0.8 means 36.89 degree. Theta 2 is equal to cos inverse 0.71, like we can write it like cos inverse 0.707. So that will give us 45 degree. Now what is the phase angle between our IBA and our, if we just do it, what we will get, the vector IC dash A, like if you just subtract it, then you will get it. You will be find it like there will be 8 degree, there will be a phase difference of 8 degree. So how to find out the angle between them, like see here, what is the angle between VCA and VAB? This angle is how much? This angle is 60 degree, right? So what is the angle between your I dash CA and IBA? Why I am interested in I dash CA and IBA is that if we go to this diagram, you will find that I dash CA and IBA, they are actually flowing through the same winding, right? You can also reach to the same conclusion with I dash BC, but then you have to change the orientation. But I dash CA and IBA, at least they are means flowing in the, apparently they are flowing in the same direction, so we can means anticipate that there is an acute angle phase difference between them. Like if we take I dash BC, there is a chance that we will get an obtuse angle phase difference. So now if that is the case, then okay, in other way what we can see that this is how much? This is 60 degree, right? So what is the angle between our where it is just a minute. So now we are interested to find out the angle between them. So VBC and they are having so we can write the angle between them is like the VBC and IBA, it is 60 plus theta 1 and this much is minus theta 2. So the total angle is will be (60° plus theta 1 minus theta 2). And what about the second one? Actually not obtuse angle, sorry, I made a mistake. It won't come obtuse angle. I can show that it is not obtuse. So I dash BA and I dash BC. I dash BC, that is making an angle this one. So how much is this? This is also 60° and this one is theta 2. So if you measure VAB, angle between VAB and I dash BC, you will get you 60 plus theta 2. So this means this one is 60 plus theta 2 minus theta 1. So now if you find them, if you put the value, theta 1 minus theta 2 will give you how much? Theta 1 minus theta 2 means it will become 52° and this one will become 68°. Things are becoming quite complicated, right? But we have to solve this problem. So current in one half of our winding, like here, if we consider C2A, it will be how much? Based on this 52°, we have to consider this angle. Similarly, the other one will be how much? I am quite sure that after, if someone is watching this video, after watching this video, he will drop a bomb on me because people are so afraid of complicated calculation. Now, what is the value of IBA in the second case? Second case it is 80, so it should be 80 by root 3. You should get 46.2. And what about ICA? That remains same, 100 by root 3 is equal to 57.8. So this way we will find out the corresponding current. One, it will get 93.6. Please check the calculation because I may make some mistake. This is very tiresome problem. So please check the calculation by yourself. Now, when it is like this, then what about the primary current? IP will be, how to determine IP? Here we will have I1 plus I1 dash. Now I1 and I1 dash, instead of they are in phase, now they are having some angle. So what is I1 and what is the angle between them? The angle between them is 8 degree. So I1, what is the magnitude of I1? It is 46.2 by 15. And what about that I2? 46, let us write separately. I1 is 46.2, so you will get some value 3.08, and the other one will be 57.8 by 30, that is 1 point. Now what would be the primary current? Again it will be means not straight one, but it is 3.08 square plus 1.93 square plus 2 into 3.08 into 1.93 into cos 8 is equal to 5 ampere, right? So let us just quickly recap this problem once again. So bank of 3 this. So you can always find out the turns ratio like for individual transformer it is 15. Obviously one question that can comes in your mind that here what is the line voltage of the primary side? Obviously line voltage should be taken 6600 into root 3 because the rating whatever we have given here, it is the individual transformer rating. Don't get confused that 6600 is the line voltage. Okay, it is the phase voltage of individual transformer. So it is clear from the phrasing of the question. So make sure that you understand the representation of the question. Had I mentioned it like a transformer bank with a transformer bank of rating 6600 by 440 volt comprises three identical transformer. In that case, you have to divide this 6600 by root 3. But when I am telling it in this way, a bank of three is three individual transformer. These three should be read as three individual transformer, each of them having this 6600 by 440 volt. Okay. Now at midpoint of this is actually this midpoint has made every thing very problematic. So we are having first case, it is the unity power factor. So what we can do is that I have drawn it here. It's quite complicated. First we have to find out the magnitude of the corresponding voltage. So what we did, I just started from KVL. If you follow apply KVL on a closed delta, you should get 0. So VCA plus VAB plus VBC is equal to 0. Then that implies VCA is equal to V can be written as VCB minus VAB. Since my memory is very poor, I just derive everything. I'd like to derive everything. Now here it is V small ca. So V small ca, similar to the previous one, we can write it like VCB minus VAB. Make sure that this fictitious delta doesn't exist in the transformer side. It is there, means it is a fictitious construction shown by this blue line, blue dotted line. Now this VCB, so VCB, if you take this triangle, triangle ABC, the outer triangle ABC and the interior triangle ABC. So the exterior triangle ABC and interior triangle, you will find that interior triangle, by exploiting trigonometric property, you can understand that side of the trigonometric means interior triangle is half of the exterior triangle voltage. Here one thing we must make sure that since this is one is operating with balanced load condition, later on I will compile or rather film a video on unbalanced load. So you will see that in case of unbalanced load, everything will become difficult. Means then another solution procedure has to be followed instead of this one. Thanks God this one is not unbalanced, because then there is a huge chance that first of all I would have made a few calculation mistake here while doing this. Anyway, so this triangle, if you take VCA, then that can be written as VCB minus VAB. So this is like, also from here also I just did some extra step here. VCA magnitude wise it is what? It is a half of VAC, but the way we measure VCA, and then actually these steps are not required. So from the construction and the trigonometry, you can directly write it. Sorry. So directly we can write it. So if this is the case, then based on that we have constructed this phasor diagram, right? And one more thing, what I mentioned, that why VAB and angle IBA, we are finding this angle theta1, because in case of your source, here transformer secondary is acting as a source. If your power factor angle is theta1, transformers or any source will view it as 180 plus theta1, right? So instead of theta means making this with respect to this voltage load, if you have VAB appearing, let me show you with a simple thing. This L denote load. So if this is V Here if it is angle theta, then here it should be how much? It is inside this, the current is going in opposite direction, but voltage remains same. So what you will get? You will get (180 minus theta 1), and obviously Vi cos 180 minus theta 1 will give you minus Vi cos theta 1. That means the exact amount of power generated by the load is consumed, the source is consumed by your load. Okay, so this is 180 minus theta 1. Now that is why we have drawn IBA making an angle theta 1. Obviously if you draw IAB, then it will be in an angle. How much will be the angle? Had we drawn this, should make an angle (180 minus theta 1). So from that we can figure out it should be IBA, right? Now we have drawn IBA, IBC, ICA. That is simple thing. Now we have also drawn VCA, VBC, VAB. VCA is exactly opposite to the base CA. VAB is opposite to VAB, capital VAB. VBC is opposite to that of VBC. Now then things becomes complicated. Here you are having this IB dash C, this is the current IB dash C. This is like IB dash C. How to understand this IB dash C? IB dash C and I dash AB, we can show that they are the same current. So they should lag this VAC by an angle, or VCA, better to say VCA, by an angle, how much? That is theta 2. Theta 2 is the angle of secondary. So theta 2. So then what we will get? VCA, and this angle theta 2 is equal to I dash BC is equal to I dash AB. Obviously, had we considered it across load, then it would have become VAC with angle I dash BC is equal to I dash AB, but here it is its transformer, it is VCA. VCA to, basically you are taking that other one, so you are getting this theta 2. Now what is happening here? So another current is what? Which one? Another current is your this one, that VBC. So what is your VBC? Yeah. So VBC, the current should make an angle IC dash I dash CA and I dash AB, that should lag it by an angle theta 2. Now when you take these two, then they will give us an I dash. So this I dash, if you subtract them, like I dash BC minus I dash CA, then they will give you I dash BA. And point here interesting to note that if we find out that I dash BA, that would also make an angle like theta 2 with our VAB. right? So now here let us proceed. So with this, another interesting thing to note is that this I dash CA, this is only getting, if the secondary turn is N2, it is getting only N2 by 2 amount of turn for its work. So N2 by 2 amount of turn, you can ask me question that, sir, here it is N2 by 2, here it is N2 by 2, why we are not considering them? So if you this question haunts you, then my answer is that try to understand that this N2 by 2, when you are trying the primary component, this N2 by 2 is being sensed by this one. But here if you try to consider this one, then it will be sensed by this one. So in this way you can understand. And then finally rest of the things are mathematics. We are getting these answers pretty complicated. Hope you enjoy. Okay, in the next means more we start considering unbalanced and other difficult configuration, things will become much more complicated.